In this video, we are going to look at the proof of the theorem that says cyclic subsets are in fact subgroups. To get started, we're going to let G under star be a group, and we're going to let little g be any element of G. And our goal is to show that the cyclic subset generated by little g is in fact a subgroup of G. And we're going to do this by using the subgroup criteria theorem. So we're going to use subgroup criteria theorem. And so what the subgroup criteria theorem says to do is it says I want to pick any two elements inside the set that I am trying to show is a subgroup, and I want to show that this funny little product, I want to show that A times B inverse belongs to my subset. So I'm going to start with thinking about what does that particular statement mean. If A and B are inside G, then if A and B are inside the subset generated by little g, then what I know is I know that A is equal to G to the K for some K inside the integers, and I know that B is equal to G to the L for some L inside the integers. And I know about exponent rules inside groups. And this particular statement here, that B is equal to G to the L, is going to imply that B inverse is equal to G to the minus L. And once I know that, I can now compute A times B inverse. That will be G to the K times G to the minus L, and using exponent rules in groups, that is G to the K minus L, but K minus L is an integer, so this is indeed inside the cyclic subset generated by G, and so we know that this cyclic subset is in fact a subgroup. It is traditional to refer to the cyclic subset generated by G as the cyclic subgroup generated by G, generated by little g. And the final thing that I want to do is I do want to say that while the proof is written in a multiplicative fashion, we have cyclic subgroups in additive groups, and they work the same way. It's just that we have to translate the notation. So a notation note. If we have G is a multiplicative group, then the cyclic subgroup generated by G is going to be made up of powers of G, and what we can think about is that this thing here will look like E, which will be G to the 0, G negative 1, G squared, G to the negative 2, G cubed, G to the negative 3, and so on. But if we have an additive group, so I'm writing G additively, then it turns out that the cyclic subgroup generated by G is going to be all of the multiples of G. And the multiples, of course, are where K is equal to Z. And this would be the group identity, which frequently will be written as a 0, but I'm just going to write it as an E here. It will be G and minus G, and then 2G and minus 2G, and 3G and minus 3G, and so on. And it's important to note that in the additive notation, 2G means G plus G, minus 3G would mean minus G plus minus G plus minus G. And so we've got 3 copies of minus G in that. And it's important to understand that cyclic subgroups work the same way in terms of how they're put together, but the notation does look different in an additively in a group that uses an additive binary operation.